Welcome to Brain Vision.
Okay, so first for this question, we need to determine the rate of heat transfer out of the gas, the combustion gas. Okay, since the rate of heat was transferred to the air, that means the rate of heat will be transferred out from the combustion gases. Okay, according to energy conservation law. So therefore, we can apply the energy balance equation here, which is E dot in equal to E dot out. If we expand it, we have Q dot in plus M dot 1 times H1 is equal to M dot 1 times H2. So Q dot in here is the rate of heat that was transferred into the combustion gases. Okay, you guys may wonder. I just said that the rate of heat was transferred out of the combustion gases. Okay, I will show you why it's transferred out, even though I put in here. Okay, so M1 dot here is the mass flow rate for the combustion gases, and H1 is the initial enthalpy for the combustion gases, and H2 here is the final enthalpy for the combustion gases. If we do some arrangement here, eventually we'll have Q dot in is equal to M dot 1 times Cp times T2 minus T1. So Cp is the specific heat for the combustion gases, and T2 is the higher temperature. I'm sorry, not higher temperature. The final temperature, and the T1 is the initial temperature. So now we know M1 dot is equal to 0.95 kilogram per second, and the specific heat for the combustion gases is 1.1 kilojoule per kilogram times degrees Celsius. And we know the initial temperature is 160 degrees Celsius, and the final temperature is 95 degrees Celsius. So now let's try to determine the rate of heat transfer into the combustion gases, which is equal to 0.95 kilogram per second times 1.10 kilojoule per kilogram times degrees Celsius, and then times 95 degrees Celsius minus 160 degrees Celsius. And this will give us the rate of heat transfer into the combustion gases is about 67, actually it's negative 67.925 kilowatts. Okay, so since the value is negative, that means it's transferring out of the combustion gases. Okay, so that's why I said it was transferring out of the combustion gases. So if it's transferring out of the combustion gases, that means it's transferred into the air. So therefore, the rate of heat transfer into the air, which is Q dot air here, should be equal to negative Q dot in. Okay, which is equal to negative 67.925 kilowatts, and this will give us the positive 67.925 kilowatts for the air. So now let's determine the exit temperature for the air, which is the outlet temperature of the air. So first we need to set up such equation here, which is Q dot air is equal to M2 dot times H4 minus H3, which is equal to M2 dot times Cp times T4 minus T3. Okay, should be Cpa here, which is the specific heat for the air. Okay, so H4 here is the final enthalpy of the air, and H3 is the initial enthalpy of the air. M2 dot is the mass flow rate for the air, and we know Cpa is the specific heat for the air, and T4 is the final temperature for the air, which is the outlet temperature for the air, and T3 is the inlet temperature for the air. So we don't know the mass flow rate for the air, but we do know the volume flow rate for the air, which is V2 dot here. And the M2 dot can be equal to rho times V2 dot. Rho is the density of the air. Okay. So we know in the question, the pressure and the temperature at that point was given. Okay, so we can express the density rho as P3 over RT3. P3 is the inlet pressure for the air, and the T3 is the inlet temperature for the air, and when R is the gas constant for the air. So if we plug in back to the equation, we eventually have Q dot air is equal to P3 over RT3 times Cpa times T4 minus T3 times V2 dot. If we do some arrangement, eventually we have T4, which is the outlet temperature of the air, is equal to T3 plus Q dot air times RT3 over Cpa times P3 times V2 dot. So we know P3, which is the inlet pressure for the air, is 95 kilopascal. And we know the rate of heat transfer to the air is 67.925 kilowatts. And the gas constant for the air is 0.287 kilojoule per kilogram per Kelvin. And we know T3, which is the inlet temperature for the air, is 20 degrees Celsius, which is 293 Kelvin. And CPA, which is the specific heat for the air, is 1.005 kilojoule per kilogram per degree Celsius. And the volume flow rate is 0.6 meter cube per second. So now let's plug in back to the equation to determine the outlet temperature for the air. So we have T4 is equal to 20 degrees Celsius plus Q dot air, which is 67.925 kilowatts. And then times RT3, which is 0.287 kilojoule per kilogram times Kelvin. And then times 293 Kelvin. Okay, the reason why I used 293 Kelvin here because it was multiplied by the gas constant here, and gas constant is with the Kelvin units in the whole units here. Okay, and then this whole thing here over CPA P3 V2, which is let me see, 1.005 kilojoule per kilogram times degrees Celsius, and then times 95 kilopascal, and then times 0.6 meter cube per second. And this will give us the outlet temperature for the air is about 120 degrees Celsius. And these are the answers for this question.